To the naked eye, the universe feels calm, a velvet ocean of silence scattered with points of light. Yet every glimmer hides chaos beyond comprehension. Somewhere in the dark, entire suns are being torn apart in moments, leaving behind flashes so intense they could outshine galaxies. What could burn so fiercely that it outshines the universe itself? In a cosmos ruled by gravity and time, there exist events so violent that their brightness shatters imagination. Eruptions that could turn night into day across millions of light years. Brightness, after all, is only an illusion of distance and perception. A candle nearby can drown a star far away. Our instruments stretch into the void, recording whispers of light that have traveled for billions of years. But some of those whispers come from explosions that once rivaled creation itself. One such moment can release more energy in a heartbeat than our sun will across its entire life. Yet, from here, it flickers faintly, a dying ember across eternity. And so, the question burns through the dark. What is the brightest object in the cosmos? The answer isn't simple, because brightness, like truth, depends on where you stand and what you dare to see. Brightness. It feels like such a simple thing, the measure of how much light something gives off. Yet in the cosmic theater, brightness is a trickster. What seems dazzling to us may be dim by universal standards, and what appears faint might once have burned with the fury of creation itself. The night sky lies. Every point of light you see is both truth and illusion. A story told across time, distorted by distance, stretched by space itself. The brightest stars may not even exist anymore. Their light just hasn't stopped arriving. To understand what brightness truly means, we must speak the language of astrophysics, the grammar of light. Scientists distinguish between luminosity and brightness, between what an object is and what it appears to be. Luminosity is the intrinsic power, the raw output of energy, the true wattage of a cosmic engine. Brightness, on the other hand, is the diluted echo that reaches us across the void. It depends not only on what the object emits, but how far that light must travel and what obstacles stand in its path. The universe is a fog of space-time, and through that fog, even the most blinding beacon can fade to a whisper. Our sun, the ordinary star that anchors our days, emits about 3.8 × 10⁻26 watts of energy every second. It's unimaginably bright to us, yet in the grand catalogue of stars, it's utterly average. To an observer near a blue giant like Rigel, the sun would seem pitifully dim, a fading spark beside a cosmic furnace. Rigel's luminosity is nearly 100,000 times that of our sun, its surface 1,000 times larger, its temperature searing beyond comprehension. Yet, viewed from Earth, Rigel is only the 7th brightest star in the night sky. It shines from 860 light-years away, its brilliance dimmed by distance. Brightness falls with the square of distance, a cruel law of the cosmos known as the inverse square law. Double the distance, and the light spreads across 4 times the area, its apparent glow a fraction of its former self. Even a supernova blazing in a distant galaxy can vanish into invisibility, its photons scattered thin across the fabric of space. Meanwhile, a humble nearby star can seem radiant, simply because its light has a shorter road to travel. The universe does not care for fairness, only geometry. To measure this dance of perception, astronomers invented a strange ancient scale. Magnitude. A star of the first magnitude is brighter than one of the second, but the system is logarithmic, not linear. Each step represents a brightness ratio of about 2.512. The brightest stars have negative magnitudes. The faintest visible to the naked eye hover around +6. The Sun in this system dazzles at 26.7, nearly blinding to human sight. The full moon sits around 12.7. Venus at its peak, 4.6. The farthest quasars, meanwhile, may glow with absolute magnitudes of 30 or more, yet appear as mere dots in telescopes. Their light spread across billions of light years. There are two types of magnitude: apparent and absolute. Apparent magnitude is what we see from Earth. Absolute magnitude is what the object would look like if placed exactly 10 parsecs, or about 32.6 light-years, away. This standard distance levels the cosmic playing field. It reveals the true brilliance hidden behind distance's deception. For example, if the Sun were placed at 10 parsecs, it would shine at magnitude +4.8, barely visible to the naked eye. But Betelgeuse, the dying red giant in Orion, would blaze at 5.6 from the same vantage point. Brighter than Venus, despite its surface cooling to a dull crimson. Brightness, then, is not truth. It's perspective. The universe we see is a distorted photograph, a projection of different epochs, distances, and powers. A star that seems steady may already have died. A faint smudge may be a billion galaxies stitched into one. And somewhere beyond the visible horizon, something burns brighter than anything we've ever imagined. Its light still racing toward us, not yet having had the time to arrive. Consider for a moment the hierarchy of cosmic light. At the bottom are the familiar. Stars like our Sun, fusing hydrogen into helium, radiating steady warmth across billions of years. Above them lie the blue giants, massive, short-lived titans whose light can bleach entire regions of space. Further still, the hypergiants, monsters like Eta Carinae, shedding mass in violent outbursts, their luminosities exceeding 5 million suns. These are the great showpieces of the Milky Way, and yet even they are dwarfed by transient cataclysms. When a star dies, it can do so quietly, cooling into a white dwarf, a cinder in the dark. But the most massive ones go out in explosions that momentarily rival creation. Supernovae. In those final seconds, the collapsing core rebounds violently, sending shock waves through its outer layers. The resulting flash releases more energy than our Sun will produce in its entire 10 billion-year life. Type Ia supernovae, born from the detonation of white dwarfs, can reach absolute magnitudes of 19.3, visible across billions of light-years. For a few days, they can outshine an entire galaxy of stars. Yet the supernova is but an overture. There are brighter things still, rarer, stranger, more violent. Some stars don't simply explode. They collapse into narrow beams of annihilation. These are gamma-ray bursts, the briefest, most luminous events known. In seconds, they release as much energy as the Sun will across its whole existence. The light we see is only the afterglow, the fading ember of a cosmic detonation whose main fury is concentrated in invisible rays. Were one to occur nearby, it could sterilize life across light years. Thankfully, they are distant. But distance doesn't diminish their glory. It only saves us from their wrath. And still, above even these, the universe offers its ultimate pyres, quasars. At the centers of young galaxies, supermassive black holes gorge on infalling gas. As matter spirals inward, friction heats it to unimaginable temperatures. The resulting accretion disk shines brighter than the combined light of all the stars around it. Quasars can emit up to 1,000 trillion times the luminosity of our Sun. Some are so distant that their light began its journey when the universe was only a fraction of its current age. To our telescopes, they appear faint, tiny points against the black. But by absolute scale, they are the lighthouses of creation, blazing at the dawn of time. If brightness were a contest of raw power, the quasar would win. But in truth, the title of brightest is slippery. What we perceive depends not only on power, but perspective. Some quasars beam light preferentially in narrow cones. If that cone points toward us, the apparent brightness skyrockets. Others are dimmed by dust or distance, their light stretched into the infrared by cosmic expansion. The universe is not a simple theater of lights. It's a hall of mirrors. The paradox deepens when we realize that brightness, like sound, can be amplified by resonance. When multiple galaxies collide, their central black holes can awaken in tandem, flooding the cosmos with energy. The resulting light may bounce, scatter, and echo through intergalactic gas, creating illusions of brightness far beyond the original source. In such a universe, truth is never just what we see. It's what we infer from the echoes. Imagine a candle flickering in a vast cathedral. From a few steps away, it illuminates your path. From across the hall, it's a dot in the dark. From another world, it may as well not exist. Now scale that candle up until it burns with the power of 10 billion suns, and you have a quasar. But if that candle hides behind dust or bends its light away, it can vanish completely, leaving behind only the faintest whisper in the radio sky. Light, no matter how bright, must still travel the long road of space-time. The light that reaches us today began its journey long before our species existed. Photons that touch your eyes tonight might have left their sources when Earth was still molten, or when dinosaurs walked the land, or when the first humans looked up and wondered. To observe brightness is to observe time. Every twinkle is an ancient message. Every glimmer a memory from an age when the universe was young. The cosmos is a museum of vanished brilliance, and we are its late-arriving guests. Perhaps that's why brightness carries such an emotional charge. It's not only a measure of power, but of persistence. The faintest photon, having traveled across billions of light-years without scattering or absorption, carries with it a defiance. A refusal to fade. It's a story of endurance, of survival through the entropy of time. To catch that light in a telescope is to witness something heroic, a spark that has resisted the dark since the dawn of existence. In this way, brightness becomes more than a number. It becomes meaning. We chase light not merely to measure it, but to feel less alone in the dark. Every star, every quasar, every distant burst reminds us that the universe, though cold and vast, is not empty. It is alive with fire, however far. And yet, there's a final twist. The brightest object in the cosmos might not be the one nearest to us. It might not even be visible at all. Some light is too powerful for our eyes to perceive, locked in spectra beyond human senses. Others are hidden behind veils of dust, or warped by gravity's lens. We may never see the true kings of brightness directly. We see their reflections, their shadows, their echoes stretched thin across time. So what is brightness, really? It's the illusion that connects us to the unreachable. It's the translation of energy into perception, of physics into feeling. It's how the universe speaks, in flashes, in whispers, in echoes that take eons to arrive. And as we trace those whispers, we begin to understand a deeper truth, that what shines most in the universe isn't just light. It's our desire to follow it, wherever it leads. Because the brightest things may not be the closest. They may already be gone, but their light still finds us, threading the darkness, reminding us that even in an infinite night, something once burned enough to be seen. The brightest things in the universe are born from its darkest hearts. From the centers of galaxies where light should never escape, fire erupts. From the jaws of gravity itself, where not even photons can survive, the cosmos ignites. It is the grandest paradox nature ever wrote. Black holes, the ultimate consumers of light, become its greatest creators. Through them, the universe performs its most spectacular illusion, turning darkness into radiance, silence into thunder, annihilation into creation. These are the titans of light. Quasars, Blazars, Hypernovae, cosmic furnaces that defy comprehension. To see one is to stare into the engine room of the universe, where matter becomes pure energy and space-time itself seems to burn. A single quasar can outshine 100 trillion stars, yet its source is no star at all, but a void, a gravitational abyss spinning faster than thought. To understand how such light can exist, we must step closer to the event horizon, into the anatomy of a cosmic paradox. A black hole by itself emits nothing. Its surface, the event horizon, is a one-way membrane where escape becomes impossible. But what happens around it transforms darkness into a spectacle. When gas and dust spiral inward, they do not fall quietly. Friction, compression, and magnetic fields twist them into a storm of unimaginable violence. The infalling matter heats to billions of degrees, forming an accretion disk that glows across every wavelength: radio, optical, X-ray, and beyond. Here, Einstein's equations become choreography. The disk spins near light speed, magnetic lines tangle and snap, and twin jets of plasma erupt from the poles, beams so focused that they pierce through galaxies. These relativistic jets can stretch across millions of light-years, like cosmic searchlights sweeping the void. Within them, charged particles accelerate to near the speed of light, emitting gamma rays that make even supernovae look tame. What we see as a quasar is the luminous side effect of gravity's feast, the radiant scream of matter being devoured. The first of these impossible lighthouses was discovered in 1963. Astronomers, studying a strange radio source named 3C 273, noticed something odd. It looked like a star in visible light, but its radio emissions were unlike any known stellar object. When Martin Schmidt analyzed its spectrum, he found familiar hydrogen lines, but shifted far into the red. The amount of redshift implied that it was billions of light-years away, and if that distance was correct, the object must be radiating hundreds of times the light of an entire galaxy. Humanity had just glimpsed its first quasar, a quasi-stellar radio source. That discovery shattered complacency. Until then, galaxies had been seen as the universe's largest units of light. Suddenly, astronomers realized that the centers of some galaxies were burning with a ferocity that dwarfed all their stars combined. These were not ordinary nuclei, but active galactic nuclei, powered by supermassive black holes millions or billions of times the mass of the Sun. The idea was unthinkable at first. How could something that traps light produce so much of it? But the evidence was relentless. The accretion process explained it. Gravitational energy transformed into radiation. As matter fell inward, roughly 10% of its mass converted into pure energy, 100 times more efficient than nuclear fusion inside stars. No engine in the universe comes close. What we call a quasar is not the black hole itself, but the furious halo of light surrounding it. An inferno of plasma and magnetic fury. Imagine a city made of fire, orbiting a hole in reality. That's a quasar. It spins, pulses, and flickers as it devours its galaxy's heart. Some quasars are so bright they can be seen from the edge of the observable universe. The photons that reach us today began their journey when the first galaxies were still forming, carrying news of a time when space was only a few 100 million years old. Through them, we see the young cosmos blazing with hunger, creation and destruction fused into one. Not all quasars face us directly. When their jets align with our line of sight, they become something even more extreme. Blazars. In these rare orientations, the relativistic jets point almost straight toward Earth, their energy boosted by the effects of relativity itself. The phenomenon is called Doppler beaming. Because the particles are moving toward us near light speed, their radiation is compressed and intensified. The result is a beam of light so fierce that it can outshine all other sources in its galaxy combined. Blazars are unpredictable. They flare without warning, spiking in brightness by factors of 10 or 100 in days. Their light curves dance with chaos, rapid variations that suggest the energy originates from regions no larger than our solar system. The jet acts like a cosmic lighthouse, sweeping the universe with its deadly brilliance. When we detect one, we are looking straight down the barrel of an extragalactic gun. For decades, astronomers catalogued quasars and blazars, mapping their distances, studying their polarization, measuring their X-ray emissions. Each one seemed to tell the same story. A supermassive black hole feeding on gas and stars, turning gravity into light. Yet the deeper we looked, the more monstrous they became. Some quasars, like TON 6M18, harbor black holes over 60 billion times the mass of the Sun. The light around them spans entire galactic halos. If such a beacon were placed halfway across the universe, it would still be visible to our telescopes today. But quasars and blazars are only one breed of cosmic titan. The universe's fireworks are not limited to the steady glow of accretion. Sometimes it prefers the quick, violent burst. When a star, dozens of times the Sun's mass, reaches the end of its life, its core collapses in a fraction of a second. Gravity overwhelms all forces, and the result can be catastrophic. The outer layers rebound violently, triggering an explosion known as a hypernova. Unlike ordinary supernovae, hypernovae channel their energy into narrow jets that can pierce through the star's envelope and escape into space. If one of these jets happens to point toward Earth, we see it as a gamma-ray burst, GRB, the universe's deadliest flash. GRBs come in two varieties: short bursts, lasting less than 2 seconds, and long bursts, which can endure for up to a minute. Both release more energy in their brief lifetimes than the sun will emit over billions of years. The long ones are often associated with the collapse of massive stars into black holes, the short ones with the merger of neutron stars. In both cases, the mechanism is similar. Matter falls inward, forms an accretion disk around a newborn black hole, and launches jets at near-light speed. The first gamma-ray bursts were discovered by accident in the 1960s, when American Vela satellites were scanning for nuclear explosions on Earth. Instead, they detected flashes coming from deep space, bursts of gamma radiation that defied explanation. For decades, no one knew how far away they were. Some thought they might originate from our own galaxy. But in 1997, astronomers finally identified an optical counterpart, confirming that GRBs occur billions of light-years away. The energy implied was staggering. Among them, one event stands above the rest: GRB 080319b. Detected in March 2008, it briefly became visible to the naked eye, even though it exploded halfway across the universe 7.5 billion light-years away. For about 30 seconds, its optical brightness rivaled that of the faintest stars. If it had occurred just a few thousand light-years from Earth, it would have outshone the full moon and possibly scorched our atmosphere. In sheer luminosity, it may be the most radiant explosion ever observed. To comprehend GRB 080319b is to confront the limits of light itself. Its energy output was so enormous that, for a few moments, it outshone every other object in the observable universe combined. Yet it lasted mere heartbeats. The core of a massive star imploded, forming a black hole, and in its death throes, it sent two narrow beams of gamma rays across the cosmos. Those photons traveled for billions of years. And then, one ordinary night, they brushed against Earth's detectors, whispering of a death that occurred before our planet's crust had even cooled. There's something profoundly humbling in that. The universe does not send messages to us, and yet it does. Every photon is a courier of time, bearing witness to ancient violence. When we capture that light, we are not just observing physics, we are communing with ghosts. The bright flicker on a telescope screen is the echo of a star's final breath. These titans of light are not merely spectacular, they are essential. Without them, galaxies would be silent. The jets from quasars and GRBs sculpt the universe, distributing heavy elements, regulating star formation, and stirring intergalactic gas. They act as both creators and destroyers, seeding the cosmos with the ingredients of life, while erasing worlds unlucky enough to lie in their paths. In their violence lies balance, but there's something deeper still, a philosophical undertone to their existence. These are objects born of contradictions. Black holes, which should swallow everything, create radiance beyond measure. Dying stars, in their final collapse, emit bursts that outshine eternity. The very mechanisms of destruction become the universe's instruments of illumination. Light, in these extremes, stops being gentle. It becomes structural, an architecture of energy shaping reality itself. Magnetic fields twist space into filaments. Jets carve tunnels through galaxies, and photons hammer against interstellar gas, igniting cascades of new stars. What we perceive as beauty is, in truth, a kind of violence. Order born from annihilation. If we could stand near one of these engines, though no human could survive, the experience would defy imagination. Space would shimmer with X-rays, time would dilate, and magnetic storms would tear atoms apart. The brightness would not even look like light as we know it. It would be radiation beyond the human eye's comprehension. And yet, if we could step back far enough, that same violence would appear serene. A steady point of light in the night sky, glowing quietly against infinity. From quasars that rule ancient galaxies to blazars that fire death beams across the universe, and hypernovae that flare like brief gods before fading. The titans of light remind us that creation and destruction are not opposites, but partners. The universe doesn't waste energy, it transforms it. Every burst, every flare, every flicker is part of that endless exchange. Matter becoming energy, energy becoming memory. And yet, even quasars may not be the final word on cosmic brightness. There are whispers of stranger possibilities. Transient phenomena so brief and powerful that they may outshine everything we know, if only for an instant. Some believe there are explosions brighter than gamma-ray bursts, signals buried deep in the dark, waiting to be found. Others suspect that brightness itself has limits, that beyond a certain threshold, light folds back into gravity, collapsing under its own power. The titans of light may be the loudest voices in the cosmic symphony, but they are not its conclusion. They are the crescendo before the next revelation. The reminder that even in the universe's darkest corners, something always burns. And as we chase those flickers through telescopes and detectors, we are really chasing understanding itself. The desire to find meaning in the fire. Because, in the end, every photon tells a story of resistance, of something that refused to stay. Dark. Every atom of gold and oxygen in your body was born in a flash brighter than galaxies. It's one of the strangest truths in existence, that everything solid, beautiful, and alive comes from destruction. The air you breathe, the iron in your blood, the ring on your finger, all of it forged in the death throes of stars. Every breath carries the ashes of a cosmic explosion. Every heartbeat echoes the rhythm of a universe that creates through annihilation. The stars do not die quietly. When their fuel runs out, they collapse under their own gravity, unleashing a final outburst so violent that for a few brief moments they rival the brightness of the entire cosmos. These are the momentary gods: supernovae, hypernovae, Kilonovae, gamma-ray bursts, transients that blaze into existence and vanish in the span of a blink. Some last days, some only seconds. Yet in that fleeting time, they change everything. A star's life is a battle between two forces: gravity pulling inward, fusion pushing outward. In the heart of a living star, hydrogen fuses into helium, releasing light and heat that resist collapse. For billions of years, this balance holds, a perfect equilibrium of pressure and gravity. But nothing lasts forever. Eventually, hydrogen runs low, and the core contracts, heating until helium itself begins to fuse into carbon, oxygen, and heavier elements. The larger the star, the faster it burns, racing toward death with breathtaking ferocity. When a massive star, say 10 or more times the mass of our Sun, exhausts its fuel, fusion ceases. The outward pressure vanishes, and gravity wins. The core collapses in an instant, compressing matter into densities beyond imagination. The atoms themselves disintegrate, electrons crushed into protons to form neutrons. For a brief moment, the entire core becomes one giant atomic nucleus, a neutron star. The infalling outer layers strike this surface at a quarter the speed of light and rebound outward. In that violent rebound, energy surges outward as a shock wave. A supernova is born. In seconds, the collapsing core converts gravitational energy into light, neutrinos, and kinetic fury. The star that once glowed gently in the night suddenly erupts with the radiance of 10 billion suns. From millions of light years away, we see it as a new point of light, a guest star, as ancient astronomers once called it. To the universe, it is a heartbeat. To us, it is eternity made visible. Some of these events have been seen by the naked eye. In 1054, Chinese and Arab astronomers recorded a bright star in the constellation Taurus that remained visible even during the day. That supernova left behind the Crab Nebula, a glowing remnant of dust and gas still expanding to this day. In 1987, another supernova erupted in the Large Magellanic Cloud, SN 1987A, offering modern science a front-row seat to the mechanics of stellar death. Neutrino detectors around the world registered the ghostly particles from the collapsing core, confirming the theory of how stars die. Supernovae come in flavors. Type 2. Supernovae arise from the core collapse of massive stars. Type Ia come from smaller degenerate white dwarfs pushed beyond their limits. In a binary system, a white dwarf can steal material from its companion until it exceeds the Chandrasekhar limit, about 1.4 solar masses. At that point, it can no longer support its own weight. Carbon ignites explosively, fusing uncontrollably in a thermonuclear runaway. The entire star detonates, leaving nothing behind. These Type Ia events are so consistent in brightness that astronomers use them as standard candles to measure cosmic distances. Through them, we discovered the accelerating expansion of the universe and the mysterious presence of dark energy. But brightness has no loyalty to time. Not all explosions fade slowly. Some burn like flashbulbs in eternity's darkness. Hypernovae are the giants among deaths. When stars with more than 30 times the Sun's mass collapse, their cores may form black holes directly. The surrounding material funnels into the hole, forming a disk that ejects energy through narrow jets. These jets, when aimed at Earth, appear as the dreaded gamma-ray bursts, light so intense it could sterilize worlds. For a few seconds, the power released can exceed all other sources of light in the observable universe. If supernovae are the deaths of stars, then hypernovae are their transcendents. The matter inside them doesn't just burn, it transforms. Temperatures soar high enough to forge elements heavier than iron, a process known as R-process nucleosynthesis. In these seconds of destruction, gold, platinum, and uranium are born. Every precious metal mined from Earth was created in one of these cosmic furnaces. When you hold gold in your hand, you are holding the ashes of a dead star. But even the mightiest single star cannot match what happens when two corpses collide. In the cold dark, after a supernova, sometimes the remains survive. Neutron stars, each the size of a city but heavier than the sun. Over millions of years, they orbit one another, spiraling closer as they lose energy through gravitational waves. When they finally merge, the collision unleashes a blast unlike any other. For an instant, matter is crushed and flung apart, forming jets of radioactive debris. The explosion is called a kilonova, 1,000 times brighter than a typical nova, but lasting only days. The light from a kilonova carries fingerprints of freshly forged elements. In 2017, for the first time in human history, scientists witnessed one directly. GW170817. Gravitational wave detectors first sensed the ripples in space-time from the merging neutron stars. Seconds later, telescopes around the world turned toward the source. They saw a point of light bloom, then fade, the visible afterglow of creation itself. Spectroscopy confirmed what theory had long suggested. In that collision, the universe had minted new gold, platinum, and rare earths. Every breathless shimmer of that event was more than spectacle. It was revelation. The cosmos, in its violence, is also a craftsman. The iron in your blood, the calcium in your bones, the silver in your veins. All of it was once molten light in an explosion that lasted less than a minute. Out of destruction, form. Out of chaos, order. Out of death, the materials of life. Not all transient lights are massive or catastrophic. Some are subtle, ephemeral. The flickers of dying white dwarfs, the pulse of magnetars releasing starquakes, the flare of matter falling into black holes. The universe's brightness is a symphony of endings, each note unique, each echo fading into silence. Even the smallest flare tells a story of transformation. Hydrogen becoming helium, helium becoming carbon, carbon becoming everything else. And yet, the most profound truth of these brief events is their silence. After the blaze fades, a stillness follows, expanding clouds of dust cooling in the interstellar dark. That dust will drift for millennia, clumping and condensing until gravity gives it new purpose. From it, new stars will form, new worlds will take shape, new beings will look up and wonder where they came from. The universe burns, rests, and builds again. In the aftermath of each explosion lies creation's raw material. Supernova remnants like the Crab Nebula or Cassiopeia A are laboratories of chemistry, glowing with neon blues and crimson reds. They are gardens of fire, where radiation stirs atoms into molecules that will one day seed planets. From these ashes come clouds dense enough to birth solar systems. Our own sun, 4.5 billion years ago, formed from the remains of older stars. Perhaps a dozen ancient deaths woven into one dawn. It's an endless cycle. Stars live, burn, die, and scatter their light. Then, from their remains, new stars ignite, carrying forward the same atoms in new configurations. Every explosion writes a new chapter in this infinite recursion of existence. What we call death is merely metamorphosis on a cosmic scale. The physics behind this may be cold, but its poetry is irresistible. In each transient flash lies the most human of truths, that nothing truly ends, only changes form. The light that dies here shines somewhere else. Energy never vanishes. It transforms, from fusion to explosion, from photon to memory, from star to story. Some of these cosmic flares last less than a heartbeat. Blink, and they're gone forever. But their consequences echo for eons. The brightness of a supernova fades in weeks, but the elements it creates endure in planets, mountains, oceans, and living hearts. The fleeting becomes eternal by becoming part of everything. There is also mystery still. Astronomers detect sudden flashes that defy classification. Fast radio bursts, millisecond pulses brighter than entire galaxies of unknown origin. Some may be magnetars releasing magnetic tension. Others might be the signature of cosmic events we have yet to understand. Each one is a whisper in the cosmic static, a spark in the void saying, "I happened." The universe is not a steady flame, but a storm of flickers, a perpetual bloom and decay of light. Galaxies themselves are gardens of fire, each star a flower that will one day scatter its petals into the dark. And we, fragile creatures of carbon and starlight, are the harvest of that garden, walking testaments to the explosions that made the elements of our bodies. When we gaze at the night sky, we are not just seeing stars. We are seeing our own beginnings. The light that reaches us is not only illumination, it is inheritance. The death of ancient suns made life possible, turning oblivion into opportunity. So when you look at the faint glow of a nebula or the flash of a dying star, remember, that light is family. It is memory. It is the oldest story ever told. That existence itself is born from endings. The momentary gods may reign for seconds, but their legacy endures for billions of years. Their brightness does not fade. It evolves, disperses, becomes the seed of new worlds and the spark of new eyes to behold them. And somewhere, even now, another star is collapsing. Another shock wave is racing outward. Another instant of impossible brightness is lighting up the cosmic night, unseen by any living being, yet destined to become the dust that one day wonders what it was made of. Because that is the secret written in every atom of us. We are the afterglow of dying stars, the living memory of their light. Brightness isn't out there. It's in how we choose to look. The universe glows in colors we'll never see. Its true radiance hides not in the visible, but in the invisible. In the long whispers of radio waves, the sharp screams of X-rays, the ghostly hum of microwaves. To our eyes, most of the cosmos is dark, but darkness is only a matter of blindness. What we call light is just a narrow slice of an infinite spectrum, a tiny window cut into eternity. The brightest things in existence may blaze all around us, unseen, because we have not yet learned how to look. Our perception of brightness begins with biology. Human eyes evolved to see between wavelengths of roughly 400 to 700 nanometers, violet through red, the range where our sun emits most of its energy. This is not coincidence, but adaptation. On Earth's surface, visible light passes through the atmosphere most easily. Ultraviolet and infrared are absorbed or scattered. So, for millions of years, life grew up in a bubble of perception, seeing only what the sky allowed. To our ancestors, the sun was the measure of brightness, the flame against which all others paled. But step outside that narrow band, and the universe changes form. The night sky we know, speckled with pinpoints, becomes a roaring sea of radiation. In radio frequencies, galaxies bloom like unseen flowers. In X-rays, black holes and neutron stars flash like sparks. In gamma rays, the entire sky flickers with bursts that no human eye could survive. What we think of as brightness is only a fraction of the truth, filtered by evolution's small window. The first hint of this came in 1932, when Carl Jansky detected strange static while studying radio interference for Bell Labs. The hiss came not from storms or machines, but from the heart of the Milky Way. For the first time, humanity heard the galaxy speak, not in light, but in radio. 2 decades later, radio telescopes began to map the invisible universe, uncovering entire populations of sources that optical astronomy had missed. Some were ordinary stars. Others were something new and bewildering, compact, powerful, and unimaginably distant. Those mysterious radio points would soon be named quasars. Each technological leap has expanded our definition of brightness. Optical telescopes gave us the stars. Radio arrays gave us galaxies. X-ray and gamma-ray observatories revealed cataclysms we never suspected. In 1962, the first X-ray telescope carried on a rocket discovered Scorpius X-1. A source 100,000 times brighter in X-rays than the sun is in visible light. Yet in ordinary vision, it is invisible. Its brightness exists only for those who can tune to its frequency. The cosmos is a concert, but we have been deaf to most of its notes. Light, as we perceive it, is the interaction between energy and awareness. To see is to translate radiation into meaning. What we call bright is not an absolute property of the universe, but a relationship between photons and perception, between what exists and what we can measure. A distant quasar may emit the power of 100 trillion suns, but its light arrives so thin, so redshifted by cosmic expansion, that our eyes register nothing. Meanwhile, the moon, pale and cold, reflects sunlight 1,000,000 times weaker, yet it dazzles us because of proximity. The universe doesn't rank its lights. We do, even our instruments impose bias. Every detector has a range, a window through which reality must pass to be seen. Infrared telescopes like Spitzer or JWST reveal the warm glow of dust-shrouded galaxies, invisible in optical light. Radio telescopes like ALMA capture the faint breath of molecular clouds where stars are born. X-ray observatories like Chandra and XMM Newton map the hot plasma around black holes. Each one sees a different universe, and none sees it whole. Brightness becomes a matter of translation. What is bright in one wavelength may be dark in another. The Crab Nebula, for instance, shines modestly in visible light, but blazes in X-rays, where its pulsar accelerates particles to near light speed. The galaxy Centaurus looks like a normal elliptical shape in optical images, yet radio waves reveal twin jets stretching over 1,000,000 light-years. When we switch wavelengths, the universe redraws itself before our eyes. It's like lifting one veil after another, discovering that reality has been layered all along. But beyond science lies philosophy. If brightness depends on perception, then it is not merely a physical quality. It's a mirror of awareness itself. What we see is not the universe as it is, but as we are equipped to see it. Just as a bee perceives ultraviolet patterns on flowers that we cannot, or a snake detects infrared warmth where we see nothing, the cosmos reveals itself differently to every observer. We call our window visible light, but that's just vanity. It's visible to us. Even within humanity, perception varies. The night sky of a city dweller, washed out by pollution, is not the same as that of a traveler in the Atacama Desert beneath a pure sky. Instruments, too, create their own realities, images rendered in false colors, brightness maps scaled logarithmically, signals amplified until invisible things blaze like ghosts. Every image of a galaxy, a nebula, or a quasar you've ever seen is a translation, not a photograph. A portrait painted in wavelengths your eyes could never know. And that realization changes everything. Brightness, then, is not truth. It's a language, a way the universe speaks to us, filtered through our senses and our tools. When astronomers color X-ray data blue and infrared data red, they aren't falsifying. They're teaching us new alphabets of light. In those images, invisible radiation becomes poetry. The true brilliance of the universe lies not in its photons, but in our ability to interpret them. Consider for a moment the cosmic microwave background, the faint afterglow of the Big Bang itself. It is everywhere, filling the sky, uniform to 1 part in 100,000. Yet it is so weak that, to the human eye, it doesn't exist. If our vision were tuned to microwaves, the entire sky would shimmer with a pale orange glow, the relic light of creation. The universe is, in truth, never dark. What we call darkness is only our blindness to the frequencies still shining all around us. Even time alters perception. Because light takes time to travel, we never see the universe as it is, only as it was. Every photon is a message from the past, and the farther we look, the older those messages become. When we look at a star 1,000 light-years away, we see it as it was 1,000 years ago. When we gaze at a quasar 10 billion light-years distant, we witness light that began its journey before Earth existed. The brightness we observe is history, frozen and stretched across the void. To see is to time travel. This relativity of light extends beyond human experience. A spacecraft orbiting a black hole would see brightness differently. Near the event horizon, light curves and bends, focusing radiation into deadly beams. The same quasar seen from one angle might appear dim from another. Gravity itself can magnify brightness through gravitational lensing, where massive objects warp space-time, bending light from background sources into arcs or rings. These cosmic lenses can amplify distant galaxies 100-fold, revealing brightness that would otherwise be lost forever. Brightness, then, is not fixed. It's a dialogue between matter, space, and the mind. It shifts with distance, direction, time, and interpretation. The brightest known quasar may not truly be the most luminous, only the best aligned or the least obscured. Our telescopes, though powerful, are like eyes peering through fog, catching fragments of brilliance while the rest remains veiled. There's humility in this. For every light we detect, countless others go unseen, buried behind dust, red-shifted beyond our detectors, or hidden by cosmic horizons. The universe may be filled with brightnesses we can only infer, never witness. Some theorists suggest that entire epochs of light, the radiance of the first stars, the flashes of annihilating dark matter, may be forever beyond our reach, their photons scattered or stretched beyond all detection. It is sobering to realize that our picture of the universe is stitched together from partial glimpses. Every discovery expands the map, but leaves the edges undefined. Even our most powerful instruments, like the James Webb Space Telescope, reveal galaxies at the dawn of time, but cannot pierce beyond the cosmic fog that came before. There may be lights older than the universe we can see, trapped behind the curtain of the Big Bang, unreachable by any technology. And yet, perhaps that's what gives light its meaning. It's not universal, it's relational. Brightness is born not merely in the emitter, but in the witness. Without eyes, there is no light, only radiation. It is observation that turns energy into experience. A photon that never meets consciousness remains a ghost, a potential unfulfilled. But when it touches awareness, when it is seen, it becomes real in the deepest possible sense. In that way, the cosmos depends on perception as much as we depend on light. The act of seeing completes the story the universe began. When we look through telescopes, we are not passive observers. We are participants in a cosmic dialogue billions of years in the making. The light we capture is ancient, but the act of noticing it is new. And in that meeting, reality itself renews. Our instruments have given us new eyes. Eyes that see across wavelengths, through dust, into the past. But they've also shown us our limits. For every brightness we uncover, there are others we cannot. The universe glows in spectra that no creature may ever sense, radiating in ways beyond our imagination. Some of that light may fall forever unobserved. Beauty without witness, brilliance without audience, and yet it exists all the same. Perhaps that's the final paradox of brightness. It is both absolute and personal. The cosmos shines regardless of us, yet its meaning is born only through us. We define brightness not by photons, but by wonder. Every new wavelength we open, every signal we decode, is another curtain drawn from reality, another hidden sun revealed. And behind each curtain, more weight. Brightness isn't a fixed quantity, but a frontier. And as we keep looking, building new detectors, expanding the range of our perception, the universe keeps rewarding us with new lights, new colors, new histories unfolding from the dark. But even as we extend our reach, a haunting thought remains. Perhaps there are forms of brightness that lie forever beyond detection. Bursts of energy too brief, too alien, or too far for any instrument to catch. Light we can only infer, never touch, and so we keep searching. Not to see everything, but to understand that seeing is endless, a process without conclusion. Because the universe may not be measured in how much it shines, but in how much we dare to look. There could exist lights that don't shine, energy beyond perception, brilliance that never becomes visible. The universe, vast and ancient as it is, might still hide forms of luminosity so extreme, so alien, that the very concept of light fails to describe them. We think of brightness as the realm of photons, of things we can see, measure, or detect. But what if brightness exists in deeper forms, in the tremors of space-time, in the silent storms of neutrinos, in the pulsing intelligence of civilizations that have mastered light itself? What if the cosmos burns not only in radiation, but in meaning? As we've learned, the universe's brightest beacons, quasars, blazars, gamma-ray bursts, all arise from destruction. But destruction is only the visible half of energy. There are deeper fires, hidden beyond the electromagnetic spectrum, where even light cannot escape or be born. In that shadow realm, we begin to approach the theoretical edges of brightness, places where physics strains against imagination. Consider the most magnetic objects in the universe. Magnetars. Born from the collapsed cores of massive stars, these neutron stars cram a sun's worth of mass into a sphere barely 20 kilometers across. Their magnetic fields are a quadrillion times stronger than Earth's. Space itself around them twists, atoms stretch, and the vacuum seethes with energy. When their magnetic crusts fracture, they release bursts of gamma radiation so intense that they can momentarily outshine all the stars in their galaxy. In 2004, a magnetar called SGR 1806-20, located 50,000 light-years away, unleashed a flare that briefly affected Earth's upper atmosphere. Had it been just 10 light-years closer, it would have scorched our planet clean of life. That single pulse contained more energy than the sun emits in 250,000 years. Yet even magnetars are dim flickers compared to what might exist beyond. Theoretical physics teases us with creatures of pure speculation: white holes, cosmic strings, Planck stars, and other entities that push our definitions of brightness past the edge of comprehension. A white hole is the mirror image of a black hole, a region of space-time where nothing can enter, only escape. If such an object ever existed, it would appear as a fountain of infinity itself, a jet of energy erupting backward through time, spewing matter and radiation from a boundary where space-time bends outward instead of inward. No one has ever observed one, but equations allow for their existence as the time-reversed twins of black holes. Some theories suggest they might mark the death throes of evaporating black holes, releasing their hoarded energy in one final blaze, the ultimate cosmic exhalation. For an instant, a white hole could shine with the combined brightness of all the stars that ever fed its darker sibling. Then it would vanish, leaving nothing but a ripple of silence. Brightness in such realms ceases to be a property of photons. It becomes a property of energy itself. Energy so dense it bends reality, distorting the rules that define perception. A white hole wouldn't just illuminate, it would redefine space and time around it, turning visibility into vibration, light into geometry. The act of observing such an event might itself be impossible. The energy would erase the observer before the observation. The ultimate brightness may be, paradoxically, invisible. Beyond even that lies the speculation of cosmic strings, infinitesimal filaments of space-time left over from the universe's birth. If they exist, they could slice through galaxies like invisible blades, carrying unimaginable tension, energy equivalent to 1 billion suns packed into a thread thinner than an atom. Should two strings collide or loop, they could unleash bursts of gravitational radiation capable of warping entire regions of the cosmos. These wouldn't be flashes of light, but pulses of existence itself, ripples in the fabric of being. They'd be brightness in its purest form, energy without photons, illumination without visibility, our detectors for gravitational waves. LIGO, Virgo, Cagra, have only just begun to eavesdrop on this hidden symphony. When they recorded the first wave from colliding black holes in 2015, the event released more energy in gravitational form than all the stars in the observable universe emit in light, compressed into a fraction of a second. Yet it made no glow, no flash, no visible sign. The universe shook, but did not shine. It was brightness beyond brightness, pure transformation, unseen but undeniable. This challenges the very way we think about light. What if luminosity is not just radiation, but revelation, a transfer of energy, information, or awareness? What if the universe's most brilliant events are those that cannot be seen, only felt through their impact on reality itself? Take neutrino storms. When a star collapses, 99% of its energy isn't emitted as light or heat, but as a flood of ghostly particles called neutrinos. They pass through matter almost unhindered. Billions stream through your body every second, unnoticed. In 1987, detectors deep underground recorded a handful of neutrinos from supernova 1987A, faint messengers from an explosion that outshone its galaxy for days. Yet, those few particles carried news of a much greater brightness, invisible to our eyes. If we could see neutrinos, the night sky would blaze constantly with the silent thunder of creation. And still, there may be brightnesses stranger than any natural phenomenon. Some scientists have begun to speculate about civilizations far beyond our own, beings that might manipulate energy on stellar or galactic scales. If such intelligences exist, their signatures might not appear as light at all, but as patterns of waste heat, gravitational anomalies, or perfectly ordered radiation. Freeman Dyson once imagined a Dyson sphere, a megastructure built to harvest the total energy of a star. To an outside observer, it would look dark, absorbing visible light and re-radiating in infrared. To us, such a structure would appear paradoxically dim, even though it contained more energy than any known source. The brightest civilizations, then, might hide behind darkness. We've even begun searching for them. Astronomers scan the sky for unusual infrared excesses. Stars dimmed in visible light, but glowing unnaturally in the thermal spectrum. So far, none have proven artificial, but the idea lingers like a myth reborn, that somewhere the universe might hold lights we cannot see because they do not shine. They think. Brightness, once a measure of photons, begins to blur into something metaphysical. What does it mean to be bright when light is no longer involved? Perhaps the truest brightness is information, the capacity to illuminate understanding. In that sense, consciousness itself may be the universe's final form of light. Awareness spreading through matter, turning chaos into comprehension. Physics echoes this idea in ways it never intended. The second law of thermodynamics ensures that entropy, disorder, always increases. But consciousness, temporarily and locally, resists it. It creates structure, order, reflection. Like stars against the void, awareness flares briefly before fading. A spark of meaning in the dark. Perhaps the cosmos itself seeks this kind of illumination. The moment when it becomes aware of its own existence through beings like us. In that interpretation, every telescope is not just a tool, but an eye through which the universe sees itself. Every photon we capture, every spectrum we analyze, is the cosmos studying its own anatomy. The brightness of the universe becomes recursive. Light observing light. Energy recognizing itself. A quasar shining across billions of years might exist only so that, somewhere, a mind could one day name it. As we push deeper into the frontier of physics, the boundaries between brightness and awareness begin to dissolve. Quantum theory tells us that observation affects reality. Relativity tells us that perception shapes time and light. Together, they suggest that brightness might not be a property of the universe at all, but of the relationship between universe and observer. Perhaps every act of perception, every moment of understanding, is a kind of luminous event, a mental supernova lighting up the darkness within. In the future, we may discover energies that make even gamma rays seem primitive. We may harness vacuum fluctuations, tap into zero-point fields, or glimpse the quantum foam that underlies space-time. Each step will reveal new layers of brightness, not as spectacle, but as understanding. The universe is not running out of light. It's running out of ways for us to remain blind. And yet, there's a haunting symmetry to it all. The deeper we look, the more we realize that true brightness might be inseparable from mystery. If we ever found a source of perfect illumination, infinite energy, total knowledge, it would destroy the shadows that give meaning to light. Without darkness, brightness loses contrast. Without the unknown, knowledge loses purpose. The cosmos needs its night so that its fire can matter. So perhaps the ultimate brightness is balance, the tension between what is seen and what is still hidden. The Magnetars' flash, the white hole's eruption, the gravitational waves' whisper, all are expressions of a universe both revealing and concealing itself, forever oscillating between exposure and secrecy. In that sense, the universe's greatest brightness may not lie in photons or plasma, but in the act of revelation itself, in the ongoing unfolding of awareness, from the first light of the Big Bang to the quiet cognition of a mind contemplating the stars. The cosmos doesn't merely emit energy, it teaches. Each discovery, each equation, each moment of awe is another wavelength of understanding, another flicker in the infinite spectrum of being. Somewhere out there, perhaps, a white hole has erupted, a magnetar has flared, a civilization has lit its sky with artificial suns. We may never see them, but we can imagine them, and in doing so, we create a new kind of brightness, one born not from matter, but from thought. Because light, in the end, is not just something the universe produces, it is something it becomes, through us, through awareness, through the endless act of trying to see. And when all stars fade, when even black holes evaporate and the universe cools toward darkness, something may remain, not light in the physical sense, but the echo of understanding, the memory of brightness, the record of everything that ever burned, thought, or dreamed. That may be the final light, the one that no physics can describe, the light that doesn't shine, but knows. To find the brightest thing, we had to look into the dark. The journey began with fire, with stars that flared and faded, with explosions that briefly outshone creation itself. But in chasing brightness to its ultimate extreme, we found a truth that humbles and transforms. The most radiant things in the cosmos are born not from abundance, but from absence. Light is not the opposite of darkness. It is its consequence. Every beacon, every blaze, every burst of glory begins as collapse. Every illumination, whether cosmic or human, is a scream rising from silence. Look at the universe, and you see this pattern everywhere. Stars ignite only when clouds of darkness, vast nebulae of cold hydrogen, collapse under gravity's pull. Galaxies spin from the aftermath of invisible dark matter. Even black holes, those icons of annihilation, give rise to the brightest phenomena we know. Quasars, Blazars, jets of fire stretching across eternity. To find luminosity, we are forced again and again to peer into the void. Brightness, it turns out, is the universe's rebellion against its own emptiness. Every photon is a defiance, a refusal to remain unexpressed. The cosmos burns precisely because it can fall apart. Collapse and radiance are two halves of the same gesture. Destruction feeding creation, gravity birthing light. The deeper the fall, the greater the blaze that follows. Consider a dying star. It spends millions of years fusing hydrogen into helium, calmly burning in balance. But when its fuel runs out, it surrenders to gravity. The collapse happens in seconds, and from that implosion comes an explosion so powerful it forges new elements. Gold, silver, oxygen, life's raw material. Darkness doesn't end light. It invents it. In death, the star becomes infinite. Its fragments spread across galaxies, its essence woven into planets and beings yet unborn. Even black holes, the darkest entities imaginable, are not pure void. They pulse with hidden energy, wrapped in event horizons that warp and magnify the light around them. Some even leak, not photons, but Hawking radiation, the faint whisper of quantum fluctuations at the edge of nothingness. If you could stand outside a black hole long enough, you would watch it fade, evaporating into ghost light across billions of years. The ultimate darkness cannot escape the destiny of brightness. It glows, eventually, through patience. And what of us? These small, temporary observers on a pale blue dot. We, too, are products of collapse. Our atoms come from dead stars. Our awareness emerges from chaos, from neural storms and chemical chance. And yet, out of that randomness, something began to look outward, to wonder, to ask, to see. The same laws that created quasars also created consciousness. Both are acts of illumination, the universe learning to recognize itself. Maybe that's why we are so drawn to light. We build fires, telescopes, cities of artificial dawn. We illuminate the night not just to survive it, but to echo the cosmos itself. Inside each of us burns a smaller version of that same hunger, the need to turn darkness into understanding. Our thoughts are miniature quasars, consuming uncertainty and radiating meaning. Every question we ask is a flare against ignorance. Every discovery, a photon in the great expansion of awareness. To see is to resist the void. To wonder is to shine. There's an old poetic truth buried in the heart of physics. The more you study light, the more it dissolves into paradox. Photons have no rest mass, yet they curve under gravity. They move at the universe's ultimate speed, yet from their own perspective, time stops completely. They are neither particle nor wave, but both. Even light itself is born of tension, an oscillation between electric and magnetic fields, forever chasing equilibrium, but never finding it. In that flicker between opposites, radiance is born. Perhaps the same is true of us. We exist in oscillation between knowing and not knowing, between awe and fear, between darkness and the desire to end it. Our thoughts ripple like light waves, fleeting but meaningful, temporary but transforming. We are creatures of paradox, luminous because we are lost. When astronomers aim their instruments at the most distant corners of the cosmos, what they really study is time. Every photon that reaches us carries history, a fragment of something long gone. To see a galaxy 10 billion light-years away is to see the universe as it once was, glowing through its own darkness. We do not see things as they are, but as they were. The night sky is an archive of vanished brilliance, a fossil record of light. The universe does not hide its past. It shines it into our eyes, and yet there is a tenderness to that realization. The same way a black hole radiates through paradox, we, too, shine through impermanence. Our lifespans are brief, our understanding incomplete, our perspective fragile. And yet, we reach for the infinite. We build machines that touch the edges of the observable universe, that record photons older than our species. In that act, we echo the stars, finite matter creating infinite illumination. Maybe that's what brightness truly is. Not power, not magnitude, but persistence. Light that refuses to vanish, thought that refuses to surrender. The first photons after the Big Bang are still traveling, still expanding, still shaping what will one day become memory. The light of our curiosity may follow the same path, diffusing through time, imperceptible but eternal. In the grand equation, brightness and darkness are not enemies. They are partners in an endless cycle of revelation and concealment. Without dark matter, galaxies would never have formed. Without cosmic shadow, stars could not contrast their glow. Without the unknown, there could be no wonder. The night sky's beauty lies not in its light, but in its balance, the harmony between the seen and the unseen. Perhaps this is the final lesson of cosmic brightness. That illumination is not an escape from darkness, but its continuation in another form. What begins as collapse becomes creation. What begins as void becomes vision. The black hole becomes a quasar. Entropy becomes memory. Darkness becomes the very reason light exists. And we, the watchers, the questioners, the temporary minds caught in the infinite bloom, are part of that same pattern. Our awareness is not separate from the cosmos. It is one of its ways of burning. We are the universe reflecting upon its own radiance. Galaxies swirl like neurons in the brain of creation, Supernovae flash like thoughts in the mind of eternity. Somewhere between collapse and comprehension, the cosmos dreams of itself. Maybe that's what it means for darkness to shine, not to vanish, but to awaken. The void is not empty. It is pregnant with potential. Every silence contains the possibility of song. Every shadow holds the memory of fire. One day, all stars will die. The galaxies will dim. The universe will slide toward entropy, toward a night so complete that no new light will ever be born. Yet even then, the story will not end. The memory of brightness will remain, encoded in the particles that once danced in the fires of suns, in the ripples of space-time that once carried their glow, in whatever consciousness still lingers to remember. Maybe that final witness will not be human. Maybe it will not even be alive in the way we understand. But somewhere, in some future epoch beyond imagining, the record of light will still exist, as the faint warmth of a dying photon, or the echo of a thought that once asked, "What is the brightest thing in the cosmos?" And perhaps, in that final instant before silence, the universe will answer. Not with a flare, but with understanding. That the brightest light it ever made was never a star, nor a quasar, nor a burst of gamma rays. It was the spark of awareness, the brief, fragile consciousness that looked into the dark and saw itself reflected there. Because maybe the true light of the universe isn't out there at all. It's within the eyes that wonder. Light dies, but meaning travels forever. Long after the stars that birthed it have burned out, their light keeps going, drifting endlessly through the cold, through the expanding silence, through the thinning fabric of space. A single photon, born in the heart of a vanished sun, might still be on its journey now, untouched, unseen, carrying within it the memory of something that no longer exists. Every ray of light is an echo, a messenger from a moment that once was, still searching for an eye to meet it. Perhaps, in that way, brightness itself is not a thing, but a memory. Every gleam, every glint, every shimmer is a story about endurance, a persistence that outlasts form. The universe's fires fade, but their echoes never quite stop ringing. Even when all the stars are gone, the last remnants of their light will continue their long migration through eternity, faint but undying. Like the final whispers of a song, the cosmos refuses to forget. And maybe that's the truest definition of brightness. Not intensity, not power, but endurance. The ability to be felt even after you've gone. The stars are not eternal, but their radiance endures in the eyes that once saw them, the worlds that grew beneath them, the consciousness that learned to name them. We carry their glow in our atoms, their dust in our lungs. The cosmos shines not just in the sky, but in us. We are, each of us, a continuation of that light. Stardust, animated by curiosity. The same energy that flared in supernovae now fires between neurons, making us wonder how it all began. When we look up and ask, what is the brightest thing in the cosmos? We are not separate from the answer. We are its continuation. Light doesn't stop at the edge of perception. It becomes thought, memory, meaning. The universe has always been a mirror. It shows us, again and again, that illumination is born from darkness, that every ending gives rise to new beginnings. The first stars lit up a cosmos that was once pure night. Their deaths scattered the elements that built life. And now, life itself looks back at the stars, creating a new kind of brightness, awareness, the light of understanding. If we could step outside time and look at the universe from beginning to end, we might see it as one continuous pulse, a single flash expanding through eternity. The birth of light, the rise of stars, the bloom of galaxies, the awakening of minds, all threads of the same cosmic glow. Even the darkness is part of it. The shadows are not failures of light, but its contrast, the canvas on which it paints its existence. So when the last quasar fades, when the final black hole sighs its last breath of radiation into the cold, will the universe truly be dark? Or will it still shimmer in some other way? Not with light, but with remembrance. Because every photon ever emitted will have touched something, changed something, passed its information along. The universe forgets nothing. It simply transforms. In the end, brightness is not about what we see. It's about what continues. The light of a supernova, the spark of thought, the curiosity that drives us to build telescopes and dream of other worlds. All of it belongs to the same lineage. Each is a way of saying, I was here, I existed, I burned. And that is what light truly means, to leave an imprint on the void, to make the emptiness remember. Perhaps that's why the question will always matter more than the answer. The search itself is illumination. The act of wondering keeps the cosmos alive within us. For every galaxy we map, another mystery arises. For every brightness we measure, another darkness deepens. But still we look, still we ask, still we shine. Maybe the brightest object in the universe isn't a quasar or a supernova or a burst of gamma rays. Maybe it's the mind that asks the question. The consciousness that refuses to stop seeking. The same fire that lit the stars burns quietly in our thoughts. It may not light up the sky, but it illuminates meaning. It turns the indifferent universe into a story worth telling. And when the last light finally fades, what will remain? Not the stars, not the galaxies, but the echo of that question, reverberating forever through the dark. What was the brightest thing in the cosmos? The answer, perhaps, is this. It was never just light. It was the longing to see, the memory of brightness, the thought that dared to ask,